And let's see what it looks like if you fall into a black hole with an inner horizon as well. So we do not have simulations currently for the Kerr spacetime, but we do have a proxy for that, the Reissner-Nordstrom spacetime, which is a black hole with an electric charge that has many of the same causal properties as Kerr because it has this inner horizon. So in the words of John Wheeler, charge is a poor man's angular momentum. The way that we're going to go about this, I've plotted basically the whole 4-pi view of your sky here. So if you're looking directly downward at the black hole, that's the left half of the image. The right half of the image is looking directly upward at the sky above. And I've also just want to show this navigation panel. So we have you, your flight path, the outer horizon, the event horizon is the red one. The inner horizon is this salmon color. And let's see what happens. Okay, so I've started it. We're starting off pretty slow, but slowly we'll pick up speed as we fall inward. So we can see right away, if you look at the right half, that the sky above you is red-shifted. This is a general result from general relativity. The sky below you is just a little bit blue-shifted. And as we come in, then eventually we're going to cross the event horizon. And the same thing that happened before will happen, which is that we don't actually notice anything special. The event horizon isn't a locally observable surface. Now let's see what happens when we reach the inner horizon. Okay, a bunch of weird stuff has happened. Now we're in this new region. This is actually a white hole. And now we've escaped it. And you'll see we're in a new universe. I've shown it as the same universe. You can do some topological things. But now we're just going outwards. And if you look in front of you, you'll see that this white hole that we escaped from shrinks as we go into our new universe. So this is a pretty neat animation, but I want to show you just once again that something weird happened at the inner horizon. If you notice, there were some flashes, there was some weird stuff. So let's analyze that. And the really weird thing that happened, which leads us into our discussion of accretion, is that something that Roger Penrose was the first to point out back in the 60s, which is that the inner horizon is a surface of infinite blue shift. So he pointed this out in this work, which is not on the internet, but it is in the library at the top of the Gamma Tower. So what he means by that is that if you were to fall into a black hole, follow this yellow line, for example, and then your buddy didn't want to fall into a black hole, so they just hang out outside like a normal person, then they could send you light signals. And when they do so, let's say they're sending you light signals at equal periods of time, then as they reach their infinite future, you're going to be reaching the inner horizon. And you're going to do so in a finite time, but they're going to reach the infinite future in an infinite amount of time. So what that means is as you reach that inner horizon and cross it, you are receiving an infinite amount of light from the infinite future. You're seeing the entire end of the universe, essentially. So obviously, this can't be good. Something bad is going to happen. And the thing that happens was first found in 1990. Werner Israel and his grad student, Eric Poisson, found that the full nonlinear solution was something called mass inflation. The idea that if you have any perturbations of a black hole, then they're going to blow up exponentially and diverge at the inner horizon. And so even just a single photon that you throw into the black hole will have a gravity of its own. Yes, photons have gravity because they have energy, and that gravity will end up diverging and causing a space-time to form a singularity at the inner horizon. It's called the mass inflation instability because they were analyzing this model where the mass parameter is allowed to vary over time to account for accretion. So you have non-zero m dot. And when you do this, then you find that m diverges exponentially at the inner horizon. So the external mass that you would measure from outside is still going to be finite, but as you go in is where you notice this instability. So this requires a few different ingredients. You need non-zero surface gravity at the inner horizon, but mainly you need ingoing radiation, and you also need outgoing radiation, which could come, say, from the collapsing star, which formed the black hole in the first place. But when you have that, these streams of matter will inflate through each other and will completely change the space-time after that. And so the question becomes, well, what happens beyond that? So what happens is has been a really tough thing to analyze. A lot of people have attempted over the years to figure out what happens. And one great model was first developed by my advisor about a decade ago. And it assumed a few different things. So first of all, we have axial symmetry. And second, we have conformal separability of the Hamilton-Jacobi equations and a few other technical mathematical things. But mainly, the idea is that you have a constant source of accretion. So some material which is really tiny, but is constant over time. And so if you add that to your black hole, then you come up with a solution, which the equation is a bit too long to include on this slide and wouldn't be really meaningful. But what I found when I started my PhD is that locally at the inner horizon, this solution simplifies a lot. So much that we can actually do calculations with it, which is much tougher when you have this full solution. So this metric I've called the inflationary Kasner metric. And here is what it looks like. So it's a completely homogeneous space-time, and it's caused by this evolution of this time parameter t that starts from 1, where you are in a regime where space-time still looks like the Kerr metric, say around here, and then t decreases over time to 0. And as it decreases, you can see the initiation of mass inflation. But then there is the second epoch, the collapse epoch, where the space-time bounces and collapses into a space-like singularity. So what do I mean by that? Well, there are these scale factors here, A1 and A2. They measure how much you're being stretched in the radial and the transverse directions. You've probably heard that if you fall into a black hole, you get spaghettified by these forces. That's actually only true in a Schwarzschild black hole. So if you have an inner horizon, then the opposite actually happens. So you might start out being stretched, but eventually, because the inner horizon is the surface where the inflow of space slows down again, then you'll actually get squashed down like a pancake, or you'll get pancakeified. So this is generally what we would expect for like a Kerr black hole, is that you would get squashed. But what this inflationary Kasner solution says is that initially, your radial scale factor is going to decrease, so you'll get squashed down in that direction. But after this bounce, it's going to start to increase. So you'll get stretched in the radial direction and squashed in the transverse directions, which is exactly what we would expect for spaghettification. And so the end result is that once again, you will get spaghettified. Okay, so this is the general form of this inflationary Kasner solution. So you can do things like ray trace geodesics, which I don't want to go into too much. So let me just show the conclusions of this first half then, which is that there are two different effects that we care about. First of all, you want to model the rotation of a black hole. So this generally gives rise to an inner horizon that could be modeled, say, by the Kerr metric. But the Kerr metric has a problem, and that is when you add accretion, then the perturbations from that accretion cause an instability of that inner horizon, cause all of the matter to diverge in energy density and curvature at the inner horizon. And the result of this, if you have a full globally self-consistent solution, that the inflationary Kasner model takes over. So the conclusion of the matter is that the inner horizon collapses into a strong space-like singularity. And so now we do have a model that looks like Kerr everywhere on the outside, but on the inside, then basically looks a lot more like the Schwarzschild solution. So the questions we want to ask of how to go forward with this is, what if the black hole isn't accreting anything? So this instability required accretion of at least some form. So could we simulate some black hole in the lab in the far future that is completely isolated and avoids this instability so that we can create a wormhole of our own? Or we could also ask, what about quantum effects? So this is entirely classical, but once we get to high enough energy, then quantum mechanics starts to take over, and we haven't talked about that yet. So let us talk about that. The next two slides are a bit math heavy, so I apologize in advance, but we'll get through it soon. The common thing that I hear said, repeated a lot, is that gravity is incompatible with quantum mechanics. And I think this is a myth which was first started around the 1950s and 60s when it was actually true, when we didn't really have a good way of dealing with quantum gravity in this effective field theory framework. But eventually people did work out all of these kinks and add all of the appropriate gauge fixing terms and ghost fields that you need to add. And so now I would say that you can formulate a theory of gravity that is consistent with observations and should predict new observations moving forward. So what is this theory? Well, if you have a metric, then you can split it up into a background metric, G bar, plus some fluctuation on top of that. And this fluctuation, we have a background field. In the classical case, it's a gravitational wave, but in the quantum case, we can call it a graviton, a quantum of gravity. And then you can do all of the, so you can add a quantum field on top of your metric. You can do all of the things that you do in quantum field theory that you learn about in your class. You can write down a Feynman propagator. You can draw Feynman diagrams and things like this. This was a Halloween some year, I forget. This is a penguin diagram, yeah. I was a penguin for Halloween. But we're actually not going to do anything this complicated. The only thing that we care about is one loop diagrams. So these are the so-called self-energy of a field. And if we're only dealing with one loop, then since it's an effective theory, it should be valid up to about 10 to the 19 GeV, which is a very high energy. So the Large Hadron Collider is at least, it's many, many orders of magnitude below that. And so the highest energy cosmic ray we've ever observed is only 10 to the 11 GeV. And so we should expect that this should be completely valid for anything that we would deal with in the real world. And there are two diagrams that are important. One is the loop of a graviton, and one is the loop of a matter field that you might couple to gravity. And it turns out that they are both equally important. They both contribute at the same level and order. And so for the high energy folks who are out there, I feel like I'm obligated to write down an action. Here you go. Because we are only dealing with, or because these are both equal contributions, then what that means is that we can treat the graviton as just a source of matter instead of a source of gravity or curvature, which is what it was originally. And so in what follows, we're not going to deal with the actual graviton. Instead, we are going to construct what's called a one-loop effective action that I'm not going to go into the details of. But we're going to focus on the simple case where you have a scalar field that is free and is coupled to gravity with this coupling parameter c that will basically just take to 0 because that's the minimally coupled case, and it can have a mass if you want. Right, now from this action, you can do the usual things with the least action principle. If you vary it with respect to the metric, you get the semiclassical Einstein equations. So the left-hand side is the Einstein tensor, but then the right-hand side is this new thing, a renormalized version of or a quantum version of the stress energy tensor that you would normally have in general relativity. And if you vary the action with respect to the field phi, then you'll end up getting the Klein-Gordon wave equation. And this, in the non-relativistic limit, this reduces to the Schrödinger equation with a gravitational Newtonian potential. And for a spin 1 field, this would be the Maxwell equation. So a spin 1 is a photon. Sorry? Okay, so these are the equations that we can deal with. I'll mention there's this box operator here that is called the D'Alembert. It's just a contraction of two covariant derivatives.